This is the intuition video for question 1C from the 2007 MAT paper. So in this question we're given a region to work in, 0 to 2 pi, and we're given this expression 7 sine x plus 2 cos squared x, the red curve here, and we're asked for the number of times in this region that this expression is equal to 5. So from here, from the sketches themselves, you can see we have 2 points where this is true. But how do we get here algebraically, and how do we interpret the method to get here? As you may have seen in the solution video, there's something clever we can do to this to make some headway on this problem. We've got sine x and cos x's here, and we don't particularly want both. So we know we can replace cos squared x with 1 minus sine squared x. And that will generate us a quadratic in sine, which is great. So let's plot the relevant quadratic. It turns out to be this, 7x plus 2 minus 2x squared, once you've done a little bit of rearranging. You get this. So we look at 5 and say, look, we've got 2 points it crosses, right? So we need to deal with both of those. But this one doesn't really matter. Why not? This is why not. Because this is the region we should actually be considering. Because we've got this polynomial, but we know x can only take values between -1 and 1 because x is sine theta or sine x or whatever. And so the point we had over here that was an x coordinate of 3 is completely irrelevant. So we need to look at where this curve crosses 5, which is once. So sine x equals this value gives us our solutions, which give 2 possible solutions for x itself. The final thing to note about this is if we plot the two curves, y equals 7 sine x plus 2 cos squared x in red, and y equals 7x plus 2 minus 2x squared in green, which was the quadratic we used to solve the problem, we see that round here clearly their curves aren't particularly close together. There doesn't seem to be that strong a relationship between them. But here they seem to be nearly exactly the same. That you can borderline not see where one starts and the other ends. Now, why on earth has this happened? Well, think, for small values of x, what do we know? Well, we know for very small x, sine x approximately equals x. They behave very similarly. So these quadratics, this can be put into something in the form of just a quadratic in sine x. And so if x roughly equals sine x, these two expressions will roughly be equal for small values of x. That's why you have the two curves very similar here, and as we move away, that relationship starts to not be true. Sine x is nowhere near x, and so the curves diverge from each other.